Dave, what are we doing?
We need to teach.
We gotta look for people. Okay. Hey Mitchell, do you know what shell method is?
Worst case scenario, I use a card.
Alright, next.
Shell method is.
Hey, here, go on,
Do you know what shell method is?
No. What do you want?
You don't know?
You sure? Hi Bobby. We want to ask, do you know what shell method is?
Yes.
That's not the answer we want.
Alright guys, I have a question for you. Do you know what shell method is?
Shell method, like that for volume and stuff?
Something like that. Do you know what it is?
Not really.
No?
Find that.
Alright. I have a question. Do you know what shell method is? No? Oh, okay. Since none of you seem to know what shell method is, we will now teach you. Shell method is another way to find the volume of a solid of revolution. Take this graph. It'd be very difficult to rewrite it as a function of y, so using washer method would be very cumbersome and impractical. Instead, we would use shell method. Shell method uses infinitely thin shells to calculate the volume. We know that the circumference of a circle is 2 pi r, and therefore to find the surface area of each shell, it'd be 2 pi r times the height, which is also f of x. So using 2 pi r f of x, which is surface area, if we multiply that by dx, we will get the volume of each shell. And to complete the shell method, we'd simply integrate the volume of each shell from one x-intercept to the other, and that would give us the volume of the solid of revolution. So using our trusty calculator, we get the volume of the solid of revolution using shell method. And we also get the general formula. Okay, so what's the difference between shell method, washer method, and disk method? So shell method is using these thin shells to find the volume of a solid of revolution. And there is the general formula for shell method. Now, washer method uses washers to find the volume. Okay, one thing that's important to know about washer method is that it involves two curves. You have one curve that's above and one curve that's below. So when we're writing the integral, we have to take into account a larger radius and a smaller radius. Dx, of course. Now, disk method. Disk method, unlike washer, is using only one curve, and we're summing up disks instead of washers. So we use disk method when there's only one graph, and the area on the curve touches the axis of rotation. Therefore, disk method involves only one radius. That was the wrong marker. Let's do an application of shell method. For application, we're going to calculate the volume of a donut. So first we need the dimensions of our donut, the thickness and the diameter of the inner hole. And of course, the tastiness. How's it taste, David?
It's alright.
Would you rate it?
5 out of 10.
cheap donuts. So we need to find a graph that represents a cross-section of our donut. To do so, we have a circle, but we need to find how much it's translated to the right, which is half the inner hole diameter plus half of the thickness. Perfect. Then we get the equation that represents the cross-section of our donut. The radius of this cross-section is half of the thickness, and we use a calculator to find that radius squared. Here's the general formula for shell method. We're going to integrate from A to B the volume of each shell. First, we need the height of each shell. To find the height, we isolate y and multiply that by 2. This will give us the height across our cross-section. Yeah, that's the height we're talking about. Next, so these are the three-dimensional drawings of the shells that we're integrating. Plug in all our values, we will get 4 pi integral from a to b times x times the height, and of course dx. You can integrate that by hand, but we're going to use a calculator, and the volume of the donut turns out to be 13.049 cubic inches. According to Google, the volume of a similar torus is the same. Alright guys, thanks for watching. Well, I hope you actually learned something about shell method. So next time some random person comes and asks you if you know what shell method is, do say yes. Alright, big thank you to Mr. Walls for his Kylo Ren, and Mr. Jam for everything in the physics classroom, and of course Mrs. Shack for that inspiration.